Hello, it's Keith here, and this is lesson 2 of the MaxTile series of my Z80 assembly programming tutorials. What is MaxTile? Well, MaxTile is what you can see here. It's a multi-platform software and in some cases hardware tile map. It allows for scrolling, it allows for X, Y, flip and combinations of both. It allows for filled tiles, which are faster to draw, double height tiles, which save pattern data, scaling the data. And it also allows for simulated transparency where bytes that are 0 are not drawn to the screen. Now this is the midpoint test. Basically this is allowing for scrolling, it's using the cache. It doesn't allow for the most advanced functionality. One thing is that really there should be a drawn border around here because the half tile movements leave some graphical glitches around the edges. And there is a more advanced functionality like using LDIR to quickly scroll the screen that are not enabled in this. So this is considered a medium example, not the most advanced one, but this is really sort of adequate for proving that the code works and showing what it's capable of. So we're going to look at the common code that is common to all of the platforms of this example, and that'll help us understand what the modules of MaxTile actually do. So let's go over to our code and let's take a peek. Over we go. Okay, so this is the file we're going to be looking at today, and we're going to go over all the parts of this code. So at the start of execution of the example, basically you will see that somewhere in our code we have, after we've done the initialization for the platform, we run test2, which does the rest of the initialization. So the first thing we're doing here is we're setting the default scrolling position of the tile map. Background tile map base should point to the memory address of the base of the tile map data, the source tile map, and we also need to set the width 36 times 2, there's 2 bytes per tile, 36 because there's 32 visible tiles on the screen and we have 4 tiles for scrolling purposes. You can actually see the source tile map here. This is the background tile map, 2 bytes per tile, as you can see. There are also miniature tile maps for the simulated sprites here. The player sprite is actually generated from this template here, which is just using a single byte per tile. MaxTile needs 2 bytes, so this has to be converted via what's referred to as an expander, and we'll see that in a moment. So here we're setting up the tile map, and here we are indeed expanding that tile map. So we're specifying the width and height of the tile map in IY here. We are specifying the base. This is an offset that's added to the tiles, those 1 byte tile numbers. And we are specifying the source template and the destination, which is a cache in memory basically. Now this version is just expanding the tile map as is, but there's an alternate version that allows for flipping of the tile map, and that will also all be calculated automatically. Now, what we're doing next is we're initializing the crop variables. We need to set up the crop according to what we're actually trying to do. Now, if we're trying to calculate the background area of the sprite, we need one set of parameters here. If we're calculating the drawing area, we need a different set. So that's why we're doing that here. We're just initializing that. We will actually set that up later on as well when we're actually doing the jobs we need. Now, what we're going to do next is we're going to calculate the caches for the background area that the sprites actually contain. Whenever our sprites move, we need to remove them from the screen and then redraw them. So before we move our sprites, we're calculating the background area that the sprites are containing here with this routine here. So that is just getting things ready so that when our sprite moves, we can remove it. MaxTile can only draw 1 full tile. So while it can shift a tile by 4 pixels or 2 pixels, the tiles have to be a full 8 pixels. And so we can't draw half a tile at the edge of the screen. So we have to have some kind of fill routine to hide over that fact. For optimization purposes, the code is programmed to only draw in certain positions and only draw 8 pixels wide and tall tiles. It can't draw half tile versions. It would get much slower if the code was allowed to do that, or there'd have to be multiple versions, so we don't have them. Now what we're doing here at the start of our loop is we're simply moving the CPU control characters here. They move automatically. We're then reading in from the joystick and moving the player character. The X and Y position is in B and C here. Now we're then checking the fire button. If fire button is pressed, we are altering the flip mode of our player character here in the accumulator. This should be 0 to 3. And then we're using expand tile map A, and the A is the flip mode. Now we'll look at expand tile map later on, but it's basically converting that 1 byte per tile into a 2 byte per tile. It's setting the flip mode, and it's, as required, reading through that source tile map data backwards to perform the flip. So that's what that's doing. The remaining code here is scrolling the background tile map by either 1 full tile, half a tile, or a quarter tile, depending on what the hardware is capable of. If we've got something that is referred to as speed scroll, then what we are doing here is we're removing the sprites from the screen and then running set speed scroll. This is an advanced scrolling routine which uses LDIR to do a fast memory copy. Basically, if we know that one tile is 2 bytes and we've moved one tile to the left, we can do an LDR copy backwards through the the screen data, and it's quicker to do that than it is to redraw each of the tiles one by one. It's very complicated though, because what we need to do depends on the hardware and the direction we're scrolling. So in most cases that's not available, but if it is available, we need to actually remove the sprites because they may not have moved, and then redraw the background using that LDIR and then draw the sprites again. So that's what that does. Otherwise though, what we're simply doing is we're basically going to actually calculate the scroll here, and then what we're going to do is we are going to reset parts of the tile map and tell the system it needs to draw them again. For example, if we've scrolled half a tile to the left, we need to redraw the tile on the right hand side and the bottom of the screen, and so that's what these routines are doing here. And then we're running the reset scroll here. However, if we're only moving in full tiles, we just use the simplest routine here, reset scroll here. That will do that for full tile movements. This is just for partial tile movements, which are a bit more complicated. Okay, now what we're doing finally here is we are removing all the sprites from the screen here. So these sprites have all moved every time, so we're removing them from the screen, and we're then basically going to calculate the new removal routine for their new positions here. This was using the old position calculations that were calculated before up here. However, we need to calculate them for next time, so that's what we're doing there. Once again, we are clearing the board as required. We're updating the player's position here, and we're then just going into our infinite loop here. Now here we've got a routine called move player sprite. This handles the movement of the player. It basically just updates the BC coordinate and removes the sprite from the screen here. And we just run this every time, whatever direction the player moves, we need to run this. So we've just got a common routine there to save some code. So that's what that's doing. Now, when we're drawing the screen, this routine is executed. Now basically what this does is it will update the player sprite if the player sprite has been overlapped by any of the other sprites, and then what it's doing is it is calculating the new location of the sprites, calculating the background, and then we are going to then draw them all to the screen down here. So these are the drawing routines. These are calculating the location of the sprite, any cropping. By doing this as two separate parts, we're reducing the amount of time the drawing takes. So again, just trying to reduce any flicker as much as possible. So that's why we're doing that. Now, once we get down here, we're actually, if the caching is enabled, we're actually flushing the caches to the screen here. Now, fast drawing caches does this. We saw this in the minimal example as well, if you saw last week's. Get cache IY will calculate the address of the next cache in the table. The table should be loaded into IY here, and this will return a 0 if there is nothing to draw. Otherwise, we're running process cache to draw the contents of that cache. The screen is split into 3 caches, and each of those is drawn separately. When we do our drawing routines, they go into the cache and then the cache is flushed. By doing this, we can reduce the flicker potentially to nothing if we synchronize with the raster beam. So that's why we're doing that. It saves using double buffering. It's more complicated, but it saves an awful lot of memory. Double buffering, you need an entire screen buffer. This just needs about 256 bytes for each of the 3 caches. So it's much less memory. Recalculate scroll is going to calculate the new position of the background. So basically what we're doing is we're taking the source tile map address, the X and Y offset, and we're adding the X offset in tiles. We've got 2 bits that we're ignoring at the bottom there for quarter and half tiles. We're calculating the offset in tiles here and multiplying it by 2 bytes per tile and adding that, and then we're calculating the Y offset multiplied by the bytes per line here and adding that. So that is calculating the offset to the tile data source data. Set scroll, this is actually going to recalculate the scroll position. It's going to reset the tile map if double buffering is disabled. This sets the dirty flags defining that everything needs to be redrawn, and then the actual CLS routine here will actually redraw the background into the cache or to the screen. To the screen RAM directly if double buffering is enabled, because if double buffering is enabled, we're assuming we've got some hardware double buffer. Otherwise, we're going to use that cache. Now, reset scroll here, this will basically redraw the background. So what we're doing here is we're calculating the scroll. We're then going to run this reset tilemap shift routine. Now what this does is, this is assuming we've moved one full tile, and it's comparing the old position and the new position and seeing if the two tiles in those positions are the same, because if they are, and we've moved one full tile, then actually what's drawn to that position on the screen is the same as what we wanted on the screen, so we don't want to redraw it because it'd be a waste of processing power. So what we're doing here is we're checking and comparing the two. Now we're ignoring the bottom bit here because that is the update, the dirty bit there, so that is not actually defining the tile number, that's just defining if the tile wants to be redrawn or not, so we're ignoring that. And then if we find that this tile does need to be redrawn, we're setting that bottom bit to flag this tile as needing redrawing next time. Otherwise we leave it alone, and that means it's probably not going to be redrawn, and that means we will save a little bit of drawing time, because redrawing the tiles to the screen in software is very slow, unfortunately, on most of these systems. Now prep sprite IX, this just does the jobs that we need to do to get a sprite ready to draw. So what we do is we're calculating the crop position of the sprite for drawing. If it's partially off screen, we need to calculate that. We need to calculate the VRAM destination. So that's doing all of that. Zero sprite in cache is zeroing the background, is clearing the update flags for the background behind the sprite. It saves some processing power. I don't want to draw things for the background and then draw over them again for the foreground. So that's what that does, that ignores that. And then flag sprite for redraw is setting the draw flags for the sprite tilemap. The sprite is a simulated sprite. It's actually a miniature tilemap that moves around. So it also has update flags that need to be set. So that's what we're doing there. Now calc crop IX is our actual cropping routine for our sprite objects. So we load IX with the address of the sprite object, and we're loading the various parameters, the source tilemap for that sprite object, the width and height of the sprite object, the X and Y position of the sprite object, and then we're moving to the crop cache. The sprite objects have two caches. There's the crop cache for drawing, and there's the background cache for removing the sprite. So we're doing the drawing cache here. We're updating the crop parameters here for calculating the drawing of a sprite. It's slightly different for removing one. And then we are calculating the crop, and then we're calculating the background VRAM address here and loading the VRAM address into the cache here for when we actually want to draw it, which will probably be later on. Calc crop remove is for removing the sprite, so calculating the background. We've got similar stuff here. We've got some calculation routines here to calculate a slightly larger area for when our sprite has moved half a unit. We actually need to do a slightly larger area, because if the background has moved half a tile and the sprite's moved half a tile, then we need to widen the area a little bit more than if we are forcing 8 pixel movements, which are a lot simpler but a lot more ugly. So that's what we've got there. We're then moving to the alternate cache, the background cache here, and we're updating the data there. There's no VRAM destination for the background cache though, so this doesn't happen for the background, and that's because when the background needs to be redrawn, we don't use a VRAM destination, we just update the update flag within the tilemap background, and then when we redraw the tilemap background as a whole, they get updated automatically. Remove sprite IX simply moves to that background cache and then runs the remove sprite routine, which will flag the background tilemap for removal there. Finally, what we've got here is some data. So here is the background tilemap here. This is the actual tile data that is used to draw the background. It's slightly larger. You can see we've got 4 zeros here. That's because we can do a 4 tile scroll to the left, and so we need 4 extra tiles to make sure that we're not writing over something else when we're doing our updates there. And then we've got the template for the player character here. This is the 1 byte per tile template. There's a sample template for the computer controlled players here, but that isn't actually used, I don't believe, anymore. It was at one point within the code, but that's what it would look like. And then we've got the source templates for our characters here. These are the computer controlled characters. The data is slightly different here because this one is using transparency and things, so we've got different versions here just depending on how the drawing is being done. And so that is the end of the code. Now you'll notice here that these checks for SP restore, and in that case we're changing the name of the labels. SP restore is only defined if we're running from ROM. If we're running from RAM, these are just modified in RAM, but if we're running from ROM, then these are templates that will be copied to a spare area of memory. So that's why the labels are being changed if SP restore is enabled. The code uses stack misuse, and so we also use self-modifying code, but self-modifying code doesn't work on a system that runs from ROM, so SP restore has to be loaded, defined somewhere in RAM, and so that's being used as a way of checking if we're running from ROM or not. Anyway, that is all we've got for today. If you liked what you've seen, please go to the website and download the source code and the build scripts, as I always say. You're welcome to use any of the code in your own project if you can. You're welcome to use them even if your projects are commercial. This is a very, very complex example. I know it is. However, it's really all that's left to do, because I've already done the Grime Z80 example, which was a very crude Tilemap. I've done that was also in the YQuest example series. I've done the MinTile example, which was more complex but not quite to this stage. This is intended to be the foundation for any advanced games I wanted to make that were multi-platform. So it is unfortunately extremely complex. Now, what I'd suggest you do is you go to the website and download the source code, see if there's any parts that you can use, see if you can get any good ideas, or see if you can find any better ideas from learning from it. I'm not really intending you to download this and use this as is, because if you're at that stage where you are that capable, you are probably capable of writing something at least as good as I have done, and if you've written it yourself, it will be entirely tuned to your requirements, and you will fully understand it because you wrote it. But as I say, you're welcome to use my code any way you can. I hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.